Yesterday we talked about this wave packet, about the yesterday we've talked about this wave packet, um, a configuration of the field or a particle wave by which it is transferred, it is localizedly transferred in the space. What do I mean? I mean that you never have, in real life, you have never pure plane wave. The the information or particles every time is localized. If you transfer information, you transfer it by packets, even if you're communicating by means of electromagnetic waves, you transfer the information by packets. So that's the wave packet. In the simplest any wave packet, you can decompose as it. I do not see myself. I want to see myself. Sorry. Problem that I do not see myself and I understand how do I look waving my hands. Okay. So we can decompose every signal. We can decompose every signal or every wave. Now we are speaking not about the electromagnetic wave, but about the wave of the matter, the waves of probability. We can decompose it into the pure plane waves, and I missed here. We can decompose in the pure plane waves, and f of k is amplitude of wave with wave vector k. So let's look on this. I do it in that way. Sorry. Yeah, that's better. Let's do it that way. I hope that you're familiar with such an integral. Let's take the pure Gaussian packet, which is just which is represented by such an equation. And let's calculate. So what does it mean? It means that in wave packet we have in wave packet the majority of the wave is represented by the plane waves around some wave vector, or what is the same length of the wavelength, lambda equal to 2 pi over k. The majority of the waves has this wavelength, and it has that's how the f of k can be represented. And can you guys solve this integral, so derive this integral? Let's try. That's the integral we have to solve, and we know that this kind of integral is called Gaussian integral. We know how it can be calculated and its value. We can find its value. So, sorry, I move it here. Yeah, that's it. So, what we need to do, since we have such kind of integral, we need to transfer it to that kind of integral, and it's pretty simple. You need just to make a full square here. First of all, let's change the variables in that way. I will make this k naught, subtract and add this value. So that's, you see that these two integrals are the same. Then we can what we can do, we change the can you switch off the microphone, please?
同学，哪位同学的麦没关，麻烦关一下。同学们看一下，哪位同学的麦没关。
Okay. So we make the substitution. We substitute k minus k naught as xi. So we here have xi squared. Here's xi. And this small term we can put before integral because it do not depend on psi. That's it. Okay, here we have this integral, and what we need to do is just to add some value in that way that it would be it would become the full square. Okay, we know that I will write it here. So we need to make it. Oops, what's happened? I'm sorry. Let's take it here. Sorry, I'm a bit clumsy here. Yeah, it will take just a minute. So we need to make it full square. Please say if it is too trivial for you, and I will skip this part. So minus psi squared divided by delta k squared. We make it another way. We have psi divided by delta k squared plus this term can be written in that way, 2 psi divided by delta k times delta k divided by 2 just and times x times I, and we can add, we have sorry, that's the term that shouldn't be here. Okay, and we can add, and so we have, remember that, I'm sorry for writing this simple equation, but it would be great to have it near our eyes. So we have a here, and b here. So we should add minus plus delta k over 2 xy squared and minus delta k over 2 xi squared. So that brings us to the following. I'll make it here. Yeah. 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 Plus, yeah, it should be square halved. Minus the same. Okay. This part do not depend on psi, so we can move it here, and this part can be this part can be transferred in that way. Yeah. So that's the integral we need to solve. You see that this imaginary unit I squared, it gives -1, so I will delete it and put plus here, and this expression, this brackets, it will we can, where should I put it? Okay, I can write it in the following simple way: psi divided by delta k minus delta k halved ix. What should we do is that we should change the signs. Here minus, and here I change the sign. It will bring us to the same. Yeah, I'm sorry for that mess. I will change my attitude, but the next, I think. Yeah, that's the thing we need. Yeah, and here minus, and that's okay. You see that you have this value which cancels with this value. That's okay. Delta k minus, okay, squared. So here, after this things, we have and we can delete this all these terms. So we converted this integral to such an integral, but we know that this integral gives us just pi squared pi over alpha, which is okay. I will write down that way. This integral gives us square root of pi over this delta k. You see that alpha is a coefficient near x squared, so the coefficient near xi squared is 1 over delta k. So here we write 1 over delta k, and that's our integral. So what we have here, yeah, the last one thing, this minus this imaginary unit, I will delete it here and put it over. can be solved. No, it should be minus here. Hey, there's an error during the calculation. I'm sorry. It should be minus here. Yeah, the whole integral goes in that way, and that means that if initial wave packet had was Gaussian-like packet with width delta k, note that the width of the packet comes in the denominator near the if we have the Gaussian wave packet like this, yeah, e minus k naught delta k, the k naught squared. K naught gives us the center of the packet, delta k gives us the width of the packet, or deviation, standard deviation of the values around the center. So it transfers to this kind of the same Gaussian packet, but in the real space, and having the width, you see that it's this packet. It looks like as e in minus 1/2 delta k squared x squared. We can write it. In this way: e minus 1/2 delta k squared times x squared. So, and this value is squared width of the packet. So packet width is equals to square root of 2 divided by delta k. So you see, if you initially have the packet, wave packet, which width was delta k in momentum space, or conversely in wave number space, if the width of the packet was delta k, then in real space the width of this packet would be proportional to 1/delta k. So the wider the wave packet is, in real space, the more narrower the wave packet in a real space. Maybe you know this equation. When do anybody know what is the integral dk? What is the result of this integral over the infinity, of course? The result of this integral is, if I'm not mistaken, 2 pi delta function of x. What is delta function? Delta function is the function which equals to 0 at every point except 1. At 0, it equals to infinity. X, delta function of x. And you can see that if in this integral, if you put x some value, non-zero value, the exponent of delta of this exponent is an oscillating function, and whole integral gives us 0. But if you put x equal to 0, this exponent would give us 1, the unit, and the integral over the unit over the whole infinity gives us infinity. So that's the delta function, and the delta function represents the wave packet with 0 width. So it's infinitely thin wave packet. And you can see, but this one is infinitely thick wave packet in wave number space, because what it is written here, it's ekx plus k squared divided by delta k squared, where delta k tends to be infinity. That's what is written here. So that if we transfer the wave infinitely thick wave packet, infinitely thick in space of k, in space of wavelength or wave numbers, it transfers to infinitely thin in localized wave space. You can see it in another way. If you're transferring information by some very short packages, so if you try to let's say in other words, if you have your wave with a frequency 1 megahertz frequency, if you try to put this frequency, so the period of this wave is 10 to minus 6 seconds. If you try to make a pulse that is less than which duration is less than the period, so less than 10 to minus, I'm sorry, it's minus 6 seconds. So let's take pulse with 10 minus 7 seconds pulse. In that pulse, it will have not only this frequency, but it will have whole amount other frequencies, because this packet is very, very narrow. In space and in time, it would be very, very narrow, and you cannot put if you try to make it narrow in the real space or time, it will be very, very wide in the wavelength space. So it would consist not only of this frequencies, but it will consist whole other frequencies too. Returning to our, I should move here, I think. So returning to our wave packet, you see that if in real space, if in real space you have very, very thin wave packet, what does it mean? It means that you know the position of the, if we depict the wave packet that way in coordinate space psi xt, and you have the width of this wave packet. What does it mean? It means the size of your particle, not the size, but the region in which the probability to find this particle is maximum. And inside this region, you have not zero probability, high probability to find this particle. It means that you have this particle has some uncertainty in the position, because you can find it here, here, or here with almost same probability. So we can say that the position, the probability of the position or coordinate of this particle is sorry, give me a second. I have to switch to the position or coordinate of this particle has uncertainty, and this uncertainty value of delta x equals to the delta x. If we have this kind of wave packet, we know that in wave number or wavelength space, the uncertainty of delta k would be proportional to 1 over delta x. But what is delta k? In that yesterday we have found that we have found this relationship where wavelength, that's it, where wavelengths can be, we can find the momentum knowing the wavelength of our particle, and the momentum just equals to h times k. So if we substitute delta k by delta p over h, we can find that it's some kind of mess. Delta k is proportional 1 over delta x. And we know that delta k equals to delta p over h, because you can unambiguously link the uncertainty of wave numbers with uncertainty of your momentum, of particle momentum. So that means that delta p over h proportional to 1 over delta x. And we can transfer delta p times delta x is proportional to h bar. And you see, that is very important equation. We will derive it much more rigorously today or yesterday, tomorrow. You see that uncertainty of the momentum of the particle multiplied by the uncertainty of a coordinate equals to some constant, approximately constant, which is Planck constant. So that means that if you try to measure your coordinate of the particle very precisely, so delta x tends to be delta x limits to 0, then uncertainty in the particles in the particle's momentum would be very high. So more precisely you know the coordinate of the particle, less precisely you know the momentum of the particle, and vice versa. More precisely you measure the particle's momentum, less information you have about the coordinate of this particle. So that's what we can say about the wave packet. So another important problem and is before we tried to do we approximated our dispersion law omega of k as omega as some k naught plus, so we decomposed the dispersion law up to the first order into the Taylor series, d omega over dk at some k equal k naught times k minus k naught. But what would happen if we decompose the dispersion law, if we account for additional contribution to the dispersion law? So what is linear dispersion law? It's just omega of k. So we assume this this kind of dispersion law. Do you know, probably, I hope everybody knows, what is the dispersion law of the light in the vacuum? So answering for you, I say that we know that in the vacuum, the frequency of the light times times the wavelength equals to speed of light. So we know that if nu is omega divided by 2 pi, and lambda equals to 2 pi divided by k. This one gives us omega divided 2 pi times 2 pi divided by k. We can cancel it, equals to c, and we can find that omega equals to k times c. So the light in the vacuum has perfect dispersion law. It's perfect linear dispersion law. It's like this. It's like this. But, however, if you put the light through some media, it is very important. It is extremely practically important case is the transferring light through the glass, because all our internet goes through the, not all, but the magistral lines go through optical lines. And what is optical lines is just going the light through the glass fibers, and in the glass the dispersion law is not linear. It somehow deviates from the linear law, and now we can it is important to understand how it is practically important to understand how the wave packet how it behaves in the media, which can which is nonlinear media, which disturbs the linear dispersion law. Okay, before that, so we can we assume that dispersion law is this one. First of all, we should find out what does this derivatives, what is the physical meaning of these derivatives. If we assume that we have not a light wave but a particle wave, we know that d omega over dk equals to dE over dP, because we know that E equals to h bar omega and P equals to h bar k. So d omega over dk equals d over dp, but dE over dP from classical mechanics, we know it's that is just a moment. It's just a velocity, which in the simple case just momentum divided by mass. What about the second derivative of the omega over dk? We for free moving particle. For free moving particle, if we substitute omega, by E divided by h, we see that the second derivative, d omega dk squared equals to d h by d p over h squared. It equals it equals to here we have h dE over, and here h squared, which comes from here, over dP squared, but dE over second derivative of the energy with respect to momentum for free moving particle. We know that kinetic energy is just p squared to m, so the second derivative of the is just a mass, 1 over mass. So here we have h divided by mass. So that's it. And the third derivative equals to 0, because for free particle the dispersion law, the dependence of the energy on the momentum is quadratic. So we substitute these for convenience, the first and second derivatives by their physical values for free moving particles in that way. And we can substitute this dispersion law into the integral and that would give us the following integral. Remember that we had this kind of integral. We had f of k minus k naught times e chi x minus omega t, and we should instead of omega we should put it this long expression here, and then we, as usually, make a substitution: psi equals chi minus chi naught, and it brings us to the following equation. This term do not depend on the psi, and the only term that depends on psi is here. So it's it is most general form that we can have without substituting the particular form of the wave packet in the wave number space. In the previous problem, we have neglected this term. We assume that is either there is no this term, or this term is very, very small. At what conditions we can neglect this term? Here we analyze these conditions. Psi squared. What is psi? If f of xi is localized in wave space, is a localized wave packet with width delta k, so we can say that psi equals, we can estimate psi as delta k. So we substitute psi by delta k, and we say that if we want to neglect this this term, we need to this term to be much less than 1. Okay, let's then substitute the delta k by delta p, knowing that p equals to hk, and k equals to pi divided by h. We obtain the following equation. Then we know from the previous problem, we know this uncertainty relation that delta p times delta x is approximately equals to h bar, and we can replace delta p by h bar divided by delta x. Okay, we replace it. Even simpler, we can divide it by h. So this one can be replaced by delta x, and we obtain the following equation: delta x squared m over h delta x squared is much less than I have to explain it a bit more detailed. So here we have h over m 1 over delta x squared much less than 1. Then we transfer delta x here, we get h over m multiplied by time is much less than delta x squared. So what we do next? I'll make it one more time. I'm sorry. So let's write this h over m delta p over h times delta p over h times t much less than 1. This one we replace by delta x. Delta p we replace by m times delta v, which is the velocity. And then we get h over m, m times delta v divided by h. Delta p over delta h is replaced by delta x, by 1 over delta x, 1 over delta x, time much less than 1 delta x. So we cancel mx and we find that delta v times t much less than delta x. And what we see, we see that if we want to neglect this term, means that over time, the left side of this inequality, it rises in the time. So if uncertainty in the velocity is constant over the time, this term increases linearly with time. And that means if we want to neglect this term, the uncertainty in the position of the particle should increase. So delta x should be much, it should increase. That means that during the time, the wave package should spread in the time. And we can see it by analysis of the wave packet, which initially had the following form. I don't know, maybe we can, I think I will make it homework for you. I will send the homework for, I will send after the lesson, I will send this homework, and your homework task would be to analyze the dynamics of the wave packet that had this initially had this shape. So initially it was some bell-like shape, and your task would be to derive the dynamic of this wave packet, to write down how this wave packet will evolve. I will put some hints and more details in the homework. Please don't be worried. It's not just to, it would be more detailed. But I think we will skip because, if we will have the time, I will discuss the solution of this problem at the next lecture. So we'll skip this one. We'll discuss it later. That's the problem I will give you. So we discussed this wave. We discussed the wave packet, and I told you that the particle can be. Sorry, it's a million. For drawing this picture 1,000 times, we have, if we have initially the particle that can be described by this kind of wave packet, some kind of wave packet, we want what do we want? We want equation that will predict the evolution of this wave packet. We want equation that predicts the future of the particle. because in classical mechanics, we know this equation, this Lagrange equation, or if you want the Newton equation, that's the second derivative is in coordinate form, that the second derivative of the coordinate equals to force divided by mass, or if you prefer in that way, minus the derivative of the potential divided by the mass. That's the equation that governs the evolution or the behavior or the future of the particle in classical mechanics. We need the same thing for we need a similar equation for the particle in quantum mechanics. So what is this equation? First of all, we need to decide what kind of equation it would be. This equation should be, we decide that it should be the first order in the time derivative. Mathematically, what does it mean physically? It means that once you gave an information about the whole system, then you can unambiguously predict the future of the system. That means that the equation of motion, equation of evolution should be the first order, because you know that if you have, let's say, the equation of dψ by dt equals terms for some strange function of psi, you know that to solve this equation you need only the initial condition, psi at t equals to 0 gives, then you solving this equation, you will obtain the wave packet, the shape of the wave packet at any time in the future, if you know this function f, and you know the initial condition, you know the all information about your system at the beginning. So we know that is our first demand, that the equation should be linear, should be first order in time derivative. The second demand is that the equation should be linear, because we know it is a bit tricky. We know that in field theory, in electromagnetic waves do not interact each other, and that is why with each other there is a law that is called the law of superposition. You know that in electrodynamics, if you want to calculate the electromagnetic waves or electromagnetic field coming from one particle, let's see, and the second particle, you do not need to solve the problem that accounts for both particles simultaneously, but you can find the distribution of the electromagnetic field from the one particle, let's say somehow this one, then neglecting this one, then you can solve the equation for a field coming from this particle, and the okay, it would be phi1 and phi2, and the total field would be given by the sum of the fields coming from generated by both particles. Or if you work in terms of electric field strength, it's E equal E1 plus E2. So in the same way, we need this equation to be linear. I remember that, okay, so we demand two things. The equation of evolution of the particle of the system in quantum mechanics should be first order, should be the first order differential equation. Let's do it that way. And it should be, it must be linear and homogeneous. So, let's try to derive this equation. To derive this equation, we apply the energy. Let's do it that way. Spoilers. We assume that the way our particle can be, not assume, we decompose our particles into the plane waves in such way, and we know that the energy of particle equals to its kinetic energy plus actually its potential energy. Here, remember that before we decomposed the wave packet as f of k in terms of wave vector kx minus I omega t dk. But here I integrate, I work in terms not wave numbers but momentum, because we know that momentum just p equal to h bar k, so we can just substitute k by pi in this integral, and we can substitute omega, the frequency, by energy divided by h bar, and we obtain in that way the k x would comes to p times x divided by h, and omega times t equals to energy divided by h times t, and so I times kx minus I times omega t equals to I times px divided by h minus I times e divided by h times t. So that is what is written here. Now I have to give you about 10-minute breaks, and then we will derive the equation of evolution of the wave packet in quantum mechanics. We have written down this energy conservation law, or just expression for the energy. Let's look on this expression and try to take a derivative over the time of psi. What we will get? Sorry. What would be? I'm sorry. Yeah. The psi over dt equals. You see that f of p do not depend on time, so it stands as it is. Then this one do not depend on time, and the only term that depends on time is this one. But the derivative of the exponent over the with respect to the time will give us the same exponent and bring the e over h behind this exponent. So we will get minus e over h exponent I pr minus et. Yeah, that's dp. Okay, here it is written. Yeah, we can. Oh, I have forgotten I. So what about the derivative over the x coordinate? So d psi over dt, dx equals to f of p it doesn't depend. It doesn't depend on x. Yeah, guys, I'm sorry. Here, let's assume that we have the following equation here. I put it in that way. So let's assume just one-dimensional, just for simplicity, one-dimensional system where p is not a vector, but a projection of momentum on the x-axis. Dip psi over dx equals to, so this term only depends on x, and it leads us to the following: I times p and the same exponent, I by x, I would substitute x minus et dp. So we can easily transfer this one here. We find that minus I divided by h. Oh, sorry, I have forgotten about the 1 over h bar. 1 over h bar. Here, 1 over h bar. Integral f of p. E times. I'm sorry. Yeah, that's okay. I bx minus et divided by h bar. In here we cannot do that because p is the variable of the integral, and we can just put behind integral I divided by h integral f of p times p, and that's integral. Let's do not copy the same thing. Yes. So what will give us the second derivative of the p of the x? Second derivative was I would not do that job, but I would just I squared is minus 1. So the second derivative would just bring the I p divided by h one more time. So it would be I squared, which equals to minus 1 divided by h bar squared integral f of p p e with this thing p squared. Yeah. And this equation is shown here. Yeah, and here delta stands for Laplacian operator, which is delta definition is sum of second derivatives, x squared plus dy squared plus dz squared, sum of the second derivative. So this one we have proved. This one I just moved I h bar here instead of so it was as a denominator, the right hand side. I just moved it to the left hand side. Yeah, and this I squared is this minus 1. So that is the equation we just this simple equation we can get from the expression for wave packet. And as the last, if we want to multiplicate the wave packet by v of r, we can just multiplicate it. Nothing will happen. We can just do that. Then, if we summarize this term, the term 1, 2, and 3, we just multiplicate it by 2m. We will get what we will get? We will get IH d psi by dt plus minus h squared divided by 2m. I multiply it by 1 to m. Laplacian psi yeah, and plus v of r psi equals to the following thing. Equals to the following expression. Let's do the thing. I'm sorry. Let's make it -1, minus here. So here minus. It will give us minus energy here. Plus p squared over 2m plus v of r multiplied by f of b times p r minus et over h bar divided by h bar dp. What we see here? We here see the expression for the energy. You see, we already discussed that the energy equals to p squared over 2m plus potential energy. That means that this the expression in the parentheses equals to 0. That means that this left-hand side should equal to 0 too. Okay. Okay. Minus IH d psi by dt plus minus h squared 2m plus v of r equals v of r psi equals to 0. And then we transfer this term to the right hand side and we obtain the following equation. IH d psi t equals to minus h squared to m Laplacian psi plus v of r psi. We obtain so here this equation is written in more nice form. Let's do that by So that equation that we have obtained, we see that this equation has only the first derivative over the time. Here it is. And this equation is linear. You see that if psi1 is the solution of this equation and psi2 is the solution of equation, then psi1 plus psi2 is also the solution of this equation. That is the definition of the linearity of the equation. And the last thing, that this equation is homogeneous. It means that if psi equals to 0 is the solution of this equation. It means that there is a trivial solution when there is no particle. There's always a trivial solution where the psi equals to 0. But what does psi equals to 0 means? Psi equals to 0 means that there's zero probability to find the particle. You remember from the yesterday lecture that probability to find the particle around some x around some coordinate x in the region with dx or delta x as you wish equals to square root of absolute value of psi times the delta x. That's the probability to find the particle in the region near the x, yep. Delta x. So that is actually how we derived the most important equation in quantum mechanics. That is the Schrödinger equation. Later we will show that this equation is called non-stationary equation, meaning that it has the time derivative. Later we will derive the so-called stationary Schrödinger equation, which has no time derivative, but it would be discussed later. For now, that is the main equation in quantum mechanics, which governs the evolution of the particle. So once you have all information about the system, what is all information about the system? All information about the system is given by V of R. So you set the potential for the particle. And then you set the initial condition psi R0, the initial condition, potential V of R, and then this initial initial condition and potential will give you all the information about the particle's future, about the wave packet future, about how this wave packet will evolve. Actually, it is a bit you see that this delta, this triangle here, you remember that it is Laplacian operator. So, delta equals to dx. Sorry. Dx squared plus dy squared plus dz squared. So actually, this equation is the partial differential equation, and is much harder to solve than the ordinary differential equation, where you have only one variable. That's the first thing. The second thing I didn't tell you that actually, you see, as this equation is the partial differential equation of the second order in coordinate derivatives. It means that apart from the initial conditions and the V of R, the information about the system, actually you have to imply the boundary conditions. Psi or R, psi RT at some R which at some coordinates which psi at some boundary equals to some boundary gamma. It's a gamma. It's depicts the boundary of the system at t. So at every time you need to put the boundary conditions under the system. Okay. What about the boundary conditions? We will speak about it later, but usually there are two kinds of boundary condition. First one, psi at R equal infinity at any time equals to 0. So there is no particle at infinity. You have particle only at some closed region. And the another particle is that psi or r infinity t equals to plane wave. So r rp plus I omega t as in the that's the plane wave. So either you have no particles, so your particles are localized, or you're considering the plane waves, not plane waves, waves that at the infinity tends to become plane waves. So that's usually is two different boundary conditions, and they depend on the specific problem you want to solve, but we will discuss it later. Just so that's it. That's how we derive the mean equation of the quantum mechanics. We just applied the energy conservation law. We write down that the energy equals to sum of the kinetic energy plus potential energy, and that brought us, and we considered our wave packet. We decomposed our wave packet into the plane waves, integral f of p times EPR. Sorry, something happened on my tablet. EPR plus I omega t dp. So that's and combining these two things, we let's say this one, yeah, that's right. We obtain this Schrödinger equation. So, okay, now we understand what is wave packet is and what are the evolution. We understand what equations govern the evolution of this wave packet, but still we do not know how to obtain observables, how to obtain any physical quantities from our wave packets, except one thing. We know how to calculate the probability of finding the particle around some coordinate. But still, we do not know how to find the momentum of the particle, or I'd say angular momentum, or anything you want to think, the average energy. How do we do that in quantum mechanics? Given that, yes, in classical mechanics, you have the trajectory, the dependence of the particle coordinate on the time. And how do you find the momentum? In the simplest case, you can find the momentum as m times v equals to m, the first derivative of the trajectory over the time. How do you find angular momentum? Angular momentum is just is a cross product of the radius vector times momentum, or in Russian notation we denote it as RP, which is the same, but in Western notation it should be this one. So, but in quantum mechanics, we don't know. As we discussed yesterday, we do not know. We have no particle information about the trajectory. So we need some tools how to obtain physical quantities from the wave, from the shape of the wave packet, from this wave function. People usually call this wave packet wave function. So that brings us to the next part of the lecture. In quantum mechanics, instead of the dynamic variables like momentum or angular momentum are called observables. It means that the quantities, the values, the physical quantities we can observe, we can measure. They're called observables, or measure the things that we can measure. And we somehow want to extract. Usually, the wave packets before in the last in previous lecture, we discussed the wave packet in the form of the function of coordinate and time. Okay, but it's not the only way to. It is not the only way to express to describe our system. Imagine that we have some electron, or silver atom particle, some particle, which can have the angular momentum. We discussed the Schrödinger experiment, and I have shown that some particles, elementary particles, or not elementary, but microscopic particles, the projection of the momentum, angular momentum of these particles is discrete. And assume that we have some particle that has only projections plus m projection and minus m projection, only two projections, as it was in Schrödinger experiment. And this case I will denote by arrow heading up and arrow heading down. So it has up projection, up and down, and down. Okay, if we are interested only in the projections of this angular momentum, and we're not at all interested in the coordinate dependence on the coordinate evolution of the coordinate of this particle, we can represent this particle, our state, as a vector, let's say a, b, with numbers a, b, where numbers a, b in analog with this function, the a squared a, up, down, a squared gives probability of having the particle in up position, and b squared gives the probability finding the particle in the down position, and not position with up angular momentum and down angular momentum. Okay, and you see that we have to find our particle either in up angular momentum or in down. That means that a squared plus b squared equals to 1. So this I already said this word, the state, and that is the term how we depict the particle or the system in quantum mechanics. We call it the state of the particle. This state, the state completely describes the all information we can gain. I'm sorry. Completely describes all information. Knowing the state, we can get every information we can physically get from the system, but by the phrase we can physically get, I mean that indeed, if we have information about the full information about the state, we already discussed that we cannot get information about both momentum of the particle or velocity and the coordinate of the particle. You can either get information about the coordinate or velocity or momentum. That means that so the state for simplicity of notation, the state sometimes is represented by this kind of notation. This is called bra and cat notation. Now we have either this one or this kind of functions. You must understand that these notation are more abstract, is the additional abstraction over this state system, because this state, this bra state psi, can either be represented as a function psi that depends on coordinate and the time, or it can be represented as a vector AB if we are interested only in some discrete values, and all these either this or this can be represented, not can be, but people represent by simple cat notation. This vector, this thing is called bra, and this thing called cat, because together they form the English word bracket. You need to add the words letter C here. So that is bra. No, that's the cat. That's okay. Let's see. It's a bra. It's a cat. Together it's a bracket. It's called direct notations. And later, when Professor Gordev will deliver the lectures about the quantum computers and qubits, he will use these notation very widely, because it's very simple. It is simpler to write down this kind of notation than to write down either the function or the vectors. So this cat vector represents the function, and or either the function or the vector, what you want. What represents the bra vector? The bra vector. So if psi is the following, the cat psi. If you are working in the coordinate space, in coordinate representation, psi will give us just complex conjunct function. So just bra vector, bra state or vector is just a complex conjugation of the function. If you work in the vector, in the vector formalism, if your state is represented by the vector, or by, in another word, by two numbers that give you probability to find the particle either in this state or two states, the bra vector will be represented by transposed vector. It's A, B, both transposed and complex conjunct. So to get bra vector, you need to transpose and complex conjugate this vector. So if you're working with in function, with wave function, the bra is just complex conjugation, and if you're working with vectors, bra vector is both simultaneous complex conjugation and complex conjugation and transposition of this vector. So the next thing we want to say that we would very often use this this scalar product of two states, psi and phi, the scalar product. When I'm saying scalar products, you must in the moment you should understand that these scalar products gives us the scalar. So scalar means that it do not depend on the coordinate, and it should not be a vector. So if you're working in coordinate, if we're working in coordinate notations, then the scalar product will give you a psi complex conjugated, because psi is in a bra, times phi, because phi in the cat is phi is normal function, integrated over all all the volume or all the region of your interested on the system. That's it. If you're working in the vector notations, this scalar product is just a real scalar product of two vectors, bra vector, this one. I will denote it A, B, multiplicated to, let's say, if it A1, B1, it should be A2, B2. And if you're familiar with linear algebra, you can find the multiplication of these two vectors. The scalar product of these two vectors is A1 complex conjugated times A2 plus B1 complex conjugated times B2. So that is the simple thing. Actually, there are you can use people use sometimes combined representation. You can combine you can assume that if you are interested both in some discrete values, it can be angular momentum projection and coordinate, you can say that you should represent your state as a vector consisting of function A and B x t. So this numbers now is not numbers, but is a function of x, and t, and the complex and the bra vector corresponds to A complex conjugated, B complex conjugated x t, and the scalar product will give you, probably you already understand what I'm going to do. Yes, it should be A1 x t, B1 x t. Do not forget about complex conjugation, times A2 xt, B2 xt, and as the answer we need to obtain the scalar value that do not depend on the coordinate, and that means that we need to integrate this over the coordinate or over the volume of our interest. So that means that it would be integral over a1 conjugated xt times a2 xt plus b1 conjugated xt times b2 complex conjugation xt over some volume. So that is what stands for this very simple notation. So you understand why why people usually why people tend to use more simple notation, because instead of writing this cumbersome expression, you can just write psi and phi vector scalar product. So then we already have seen that some values can have some observables can have discrete values, like angular momentum projection, as in Stern and Galler experiment, or energy in the hydrogen atom. We've seen that hydrogen atom has discrete spectrum. Its energy can have only some discrete states, so it can be up or down angular momentum, or energy levels, discrete energy levels, or anything you can imagine. It's a discrete spectrum. If the system has, if the observable can have only discrete values, people usually they usually say that this value has discrete spectrum. This value has discrete spectrum, and if some observable can have continuous values, they usually say that this observable can have has continuous spectrum. Now, can you give me an example of the observables that have a continuous spectrum? Okay, the simplest observable that have continuous spectrum is the coordinate, because the coordinate can, because we can find the particle at any point of space. The another thing that is continuous is the momentum. However, the momentum can be either discrete, momentum and the energy can be either discrete, or can have either discrete spectrum and continuous spectrum. Imagine in the atom, electron in the hydrogen atom has discrete energy, but if you consider free moving electron, you'll find that the energy it can travel with a arbitrary speed or arbitrary momentum. Its energy depends on the momentum in that way, and the energy can have has continuous spectrum. But you can ask the question, what's the difference? Why in the atom electron has energy and momentum of the electron has discrete spectrum, and if they are free, they have continuous spectrum. The answer is the following: if the movement of the if the particle is somehow localized at some region, it means that the simplest way of thinking about that is the potential well, and the particle that is moving in this potential well at some trajectory. Particle cannot escape this potential well, and in this case, particle will have discrete spectrum, discrete energy values, and discrete momentum values. But if the particle is free to move all over the space, then it has continuous spectrum. So it's just a simple rule. If the particle is localized, that means that it can move only on a certain region of the space. This particle has continuous spectrum, and if the particle is delocalized, is not localized, if it can move all over the space, it has continuous spectrum of energy and momentum. So what about another another observables? Let's assume that we have some observable that we called F. And it can be either momentum or energy or angular momentum or anything you want. And let's, for simplicity, for now, assume that this observable can have only a discrete spectrum. So it can measuring, if you have this the particle, and if you measure the value of this observable, so if you measure the energy or momentum or angular momentum, you will obtain the only discrete values of this F. Let's say F naught, F1, F2, F3, and Fn. You can, in the experiment, you can find only a set of the discrete values of this observable F. For the case of Stern-Gerlach experiment, it would be it would be angular momentum projection. In that experiment, they can find only two projections, the F naught and F1. But in case of atom, electron and the hydrogen atom, you can have infinite number of energy levels. So let us denote the wave function at which we let's consider some state in which measuring if we measure the system. Okay, we have some system. We can prepare in the sense that we can attribute some state or some wave function or some vector of the state, so we can completely describe the state, and we can measure. That's the measurement box. We can measure this system, and with probability one, we will find that observable F has has the value Fn. Here we're measuring some observable, and we find, and no matter how much at any measurement, if we prepare our system to the state psi n, we will obtain the observable equal to Fn. How can we do that? For electron in the atom, we can just wait a little bit or long, and we would be pretty sure that the energy of the electron is has its lowest energy, some E naught. And no matter how much time we will measure this energy, it will have this the electron will have this energy. Or if we have some particle, we definitely know that it is in up state, so its angular momentum equals to plus m. No matter how much time we measure this state, we always obtained in our that's our instrument. It can show m. It will show minus m or plus m, and no matter how much time we will measure, we will always get this plus m. Okay, and these states are called eigenstates, and these values are called, all possible values we can measure in the experiments are called eigenvalues of this observable. So we have eigenstates, the states at which we definitely know the value of this observable, and the eigenvalues, the value of observable that we can find in experiments. Here I need to step a bit forward, because when I'm saying that at any anytime you measure this observable, you will find its value with probability 1. It means that there could be states, we discussed it when we discussed Brown-Kent notation, that we can describe our states by this vector, in which A gives the amplitude of probability finding the particle in the up state, and B gives the amplitude of probability finding the particle in the down state. So it means that we can prepare, possibly we can prepare the system in a such way that after the measurement, we wouldn't get the value of angular momentum up every time in experiments. We will get either up or down, and every time we will repeat these experiments, putting this, I will draw it here. So we have the state, state AB, put it through some measurement box, some instrument B, F, and we can have either up or down with probability equals to A squared, and probability of down equals to B squared. So that means that there could be states that can give us both up, or not both up, or either up or down. We'll speak about this phenomenon later. This phenomenon called superposition. It means that the particle is in this superposition of states up and down. It means that in the experiment you can randomly find it the system in either in up state or in down state. And this state is not an eigenstate, because in this state we cannot measure the angular momentum with probability equal 1. In this state, in this state we cannot measure the angular momentum having some value with probability 1. We have this well with this probability and this well with this probability. What would be the eigenstate in this case? Eigenstate in this case would be either 1, 0 or 1 end. Sorry. And this one. So that is the full set of eigenstates of the system that can have angular momentum either in up projection, either having plus m projection or minus m projection. That's the full set of eigenvalues, because if we measure this value, if we measure angular momentum of the system that is in this state, we with probability of getting up state is 1 squared equals to 1, and probability of getting down state is 0 squared equals to 0. So we're certain that we get our value up in this state and value down or minus m in this state. That is the eigenstates. If we look, if our observable has discrete spectrum and has only 2 possible values that we can measure. These eigenvalues, these eigenfunctions, usually they are normalized in such a way that usually they are normalized in such a way that psi n equals to 1. Let us recall what does it mean. It means that integral psi n conjunct psi n d over the whole volume equals to 1. Or you know that complex conjugated multiplied by some function is the square of the absolute value of this function. So that's it. We can write dv equal to 1. If we're interested in discrete spectrum, let's do that way. This condition will a b equal to 1. Sorry, not 0 but 1 means that a plus b conjugated b equal to 1. That means that squared absolute value of a plus scalar squared absolute value of b equals to 1. So that is the meaning of the normalization, or of the normalization. You can see that the vector 0, 1 is properly normalized because 1 squared plus 0 squared equals to 1. Yeah, that's it. So at the next lecture we will discuss how what is the mathematical attitude, mathematical approach to get the observables from the above wave function. We'll introduce the concept of the of operators, and we will discuss a little. We'll introduce the concept of operators, the concept of the eigenfunctions of these operators, and eigenvalues of these operators. So that's, I think, all for today.